The Duel of Light, Einstein, Bohr, and the Quantum Reckoning. Chapter 1. The Spark of Doubt. In the spring of 1905, a slight, unassuming patent clerk named Albert Einstein walked daily along the banks of the Aar River in Bern, Switzerland. A swirl of ideas occupied his mind: the perplexing nature of light, the seeming contradictions of Maxwell's equations, and the elusive meaning of Planck's constant. Amid the rhythmic clatter of horse-drawn carriages over cobblestone streets, Einstein mulled over the strange new possibility that light might be composed of discrete quanta, later called photons. That quiet year would soon be called his annus mirabilis, the miraculous year when the foundations of modern physics were upended by a burst of papers from a man still waiting to secure a professorship. Einstein's essay on the photoelectric effect was among his earliest breakthroughs. In it, he argued that the energy of ejected electrons from metal surfaces depended on the frequency, not the intensity, of incident light. This conclusion challenged the classical wave picture and implied that light behaved as if it were made of individual, localized particles. In the swirl of controversies that followed, Einstein would receive praise, skepticism, and confusion. But perhaps no single event foreshadowed the future debate more than Max Planck, father of the quantum concept, writing to colleagues about Einstein's audacity. Planck recognized young Einstein's genius, but wondered how far he would go in challenging the bedrock assumptions of physics. It was not for several years that Einstein's name would be internationally lionized. His work on special relativity in 1905 and, a decade later, general relativity made him a household name. Yet ironically, the 1921 Nobel Prize that Einstein eventually received was not for relativity at all. Rather, it was for that very concept of light quanta he had elaborated in 1905. That official recognition of quantum phenomena proved to be a harbinger of the deeper theoretical schism that would ultimately emerge between Einstein and the new generation of quantum physicists. At the same time, across Northern Europe, interest in atomic structure was intensifying. Planck's quantum hypothesis had offered a revolutionary way to understand black-body radiation, but the riddle extended to many phenomena. By 1909, Ernest Rutherford had proposed a planetary model of the atom, with electrons whirling around a dense nucleus. At this time, the atom was on the threshold of further conceptual transformation. Niels Bohr, a thoughtful and soft-spoken Dane, stepped onto the stage. In 1913, Bohr proposed quantized orbits in the hydrogen atom, a bold leap that explained discrete spectral lines where classical theory failed. He was initially met with confusion and at times derision from older physicists. But that did not stop the theory from catching on because it worked. Spectral lines fell into place as though a cosmic safe had been unlocked with the correct quantum combination. Einstein observed Bohr's early successes with admiration, even delight. He recognized that Bohr's quantized orbits, although strange, were the kind of radical conceptual step required to reconcile certain contradictory observations about atoms. However, Einstein remained uneasy. Already by 1913 to 1914, he was musing in letters about whether these quantum rules were merely provisional, an intermediate scaffolding to a more elegant and deterministic theory. That tension would only increase over the coming years, as the wave-particle duality and the concept of complementarity, developed by Bohr, arrived to complicate everything. In 1919, as news of the solar eclipse that validated general relativity spread across the globe, Einstein became the world's most famous scientist. Bohr, meanwhile, consolidated his presence in Copenhagen, where he directed the Institute for Theoretical Physics. It became a mecca for bright talents: Heisenberg, Pauli, Dirac, and many others, who were forging what came to be called the new quantum theory. These brilliant young physicists saw Einstein as a demigod, but also sensed that he was drifting from their circle. The older man, always the iconoclast, found the emergent quantum formalism lacking in conceptual clarity. Or more precisely, he felt that these mere mortals, the younger generation, were too quickly satisfied with a theory that lacked realism and determinism. Throughout the early 1920s, Einstein attended conferences in Europe, particularly the famed Solvay conferences in Brussels, where luminaries met to hash out fundamental problems. He would smile politely at discussions of wave functions and the perplexities of matrix mechanics. He grew acquainted with Werner Heisenberg, who in 1925 introduced matrix mechanics, and with Erwin Schrödinger, who in 1926 introduced his wave equation. Both theoretical frameworks seemed to converge on a single consistent quantum mechanics, but did so from quite different mathematical starting points. Einstein marveled at the success of these theories in explaining atomic spectra and chemical behavior. Still, as he wrote to his friend Michel Besso, "I like the idea, but I cannot believe that God plays dice with the world." During these same years, Bohr worked with a quiet but unshakable conviction that quantum theory revealed a fundamental truth about nature. The classical categories of wave and particle, position and momentum were no longer wholly valid. Reality, in Bohr's view, could only be described by a new principle he called complementarity. In essence, whether you see wave-like or particle-like properties depends on how you set up the experiment. This was no mere philosophical stance. It was mathematically backed up by Heisenberg's uncertainty principle and the success of quantum mechanics in predicting countless phenomena. For Bohr, the clarity of classical physics was a human concept. In quantum reality, clarity is replaced by a tapestry of probabilities. The notion that we could glean an underlying deterministic storyline behind quantum events was, he believed, an illusory vestige of classical thinking. Even from the earliest days of matrix mechanics, Einstein saw red flags. He did not dispute the empirical success. Indeed, he once jokingly told Paul Dirac, "They have me cornered." But while the younger generation was perhaps content to leave the theory as fundamentally probabilistic, Einstein insisted that quantum mechanics could not be the final word. There must be elements of reality unaccounted for, he would say, echoing an older philosophical tradition that demanded objective states of the world independent of measurement. In the years before the famously heated debates, Einstein and Bohr were still in warm correspondence. They had great personal affection for each other, and the letters they exchanged reveal a mutual respect despite growing philosophical differences. However, as the mid-1920s turned into the late 1920s, quantum mechanics, armed with the Born rule, the Schrödinger equation, the Heisenberg commutation relations, and Bohr's concept of complementarity, became more robust and widely accepted. Einstein grew uneasy. He confided to colleagues that quantum mechanics was correct, but incomplete. He needed a stage upon which to challenge the new orthodoxy. That stage arrived in Brussels in 1927, at the Fifth Solvay Conference, where the world's leading theoretical physicists converged to debate the frontiers of quantum theory. Chapter 2. The Oracle of Copenhagen. Niels Bohr was born in Copenhagen in 1885, the son of a physiology professor, and nurtured in an environment where both scientific inquiry and philosophical reflection flourished. Tall, somewhat stooped, with a deep voice and a characteristic penchant for pausing mid-sentence, Bohr had a gentle yet magnetic presence. He was the embodiment of the sage, quietly guiding talented young researchers who flocked to his institute. He spoke with measured thoughtfulness, often rephrasing his ideas multiple times. Some found his style impenetrable, others discovered great profundity in the slow unfolding of his words. From the moment Bohr embraced the quantum concept to explain the hydrogen atom's discrete spectra, his name became associated with a form of radical rethinking in physics. In the 1920s, many young scientists passed through his Institute for Theoretical Physics. Werner Heisenberg, a brilliant and bold German, Wolfgang Pauli, known for his acerbic wit and genius, and the shy but mathematically gifted Paul Dirac from England. Copenhagen was a hive of theoretical speculation, yet, ironically, no single Copenhagen interpretation was ever set in stone. Instead, there was a shared ethos that quantum phenomena demanded a rethinking of the classical categories of measurement, objectivity, and determinism. Central to Bohr's position was complementarity, that certain experimental setups reveal wave-like properties, while others reveal particle-like properties. Trying to unify these into a single classical picture was, in Bohr's mind, futile. Instead, the quantum world does not permit a complete, single viewpoint. This was more than a philosophical stance. It was a perspective shaped by experiment and the new mathematics of Hilbert spaces, operators, and wave functions. Bohr was not, however, a dogmatic philosopher. He was cautious. He realized that the language used to describe microscopic phenomena was borrowed from a macroscopic world. The crux of complementarity was that an experimenter's choice, how the experiment is set up, ultimately defines which complementary aspect is measured. Once that measure is taken, the other complementary property is not just unknown, but undefined in classical terms. It was a conceptual leap that Einstein found disquieting. Privately, Bohr recognized Einstein's towering stature. He read Einstein's works with reverence, especially the conceptual leaps of special and general relativity. Bohr was awed by Einstein's ability to think beyond the established frameworks. Yet he was also confident that quantum mechanics was revealing an equally profound revolution. Bohr gave Einstein credit for having first recognized the quantum nature of light, but he believed that Einstein remained tethered to an older notion of physical reality, one requiring that objects have definite properties at all times, whether measured or not. Stories told by those who knew them recount how Bohr, in the mid-1920s, would pace across his office, describing the wave function as a new form of knowledge about a system rather than a direct representation of material reality. He would stop, turn, and exclaim in near frustration, "We are suspended in language." Over the years, he honed this perspective, culminating in the viewpoint that measurement in quantum mechanics is not just an act of passive observation, but an intervention that shapes the reality one observes. For Bohr and his colleagues in Copenhagen, the success of quantum theory was so overwhelming that philosophical qualms seemed secondary. The entire periodic table, chemical bonding, the intricacies of atomic spectra, and even the basics of nuclear physics, quantum mechanics explain them all. Of course, there remain puzzles, Bohr would say, but we must accept that which cannot be otherwise. By cannot be otherwise, he referred to quantum mechanics' consistent internal logic and experimental validations. Thus, when the invitation to the Fifth Solvay Conference in 1927 arrived, Bohr was eager. He had a sense that the old guard, led by Einstein, might question the new theory's coherence. Privately, Bohr looked forward to the challenge. In his heart, he believed that if quantum mechanics was correct, then no purely classical argument could dismantle it. Yet he also knew that if anyone could find a hidden flaw, it would be Einstein. In the weeks leading up to the conference, Bohr convened a small circle of confidants: Heisenberg, Pauli, and Kramers. They pored over possible Einsteinian objections. They studied the newly formulated uncertainty principle. Heisenberg expressed particular concern, suspecting that Einstein might exploit certain aspects of wave-particle duality or time-energy relationships to find contradictions. Bohr paced in his office, hands clasped behind his back, muttering, "We must be prepared for anything. Einstein's cunning is no less than his genius." It was a half-joke. In truth, Bohr both anticipated and feared the intellectual clash. On one hand, the chance to pit his idea of complementarity against Einstein's realism was an opportunity to refine and test quantum theory at the highest conceptual level. On the other hand, there was an undeniable sense of facing a giant, a figure who could unravel entire fields with a simple thought experiment. Bohr's greatest fear was that the theory, so successful, might crumble under an Einsteinian challenge. Meanwhile, in Berlin, Einstein prepared in his own way. He jotted notes on the back of envelopes, scribbled sketches of imagined apparatuses to test the fundamental principles of quantum mechanics. He was not looking for a quick gotcha, but a conceptual wedge that would reveal quantum mechanics to be incomplete or logically inconsistent. By the time the conference approached, Einstein was ready to present a well-considered set of challenges, each carefully constructed to expose the interpretative vulnerabilities of the Copenhagen viewpoint. And so, with the stage set, the major figures of theoretical physics converged in Brussels, each with their own hopes and anxieties. Few realized at the time that these gatherings would become legend. Chapter 3. The SV Confrontations, October 1927. The fifth Solvay Conference convened at the Metropole Hotel in Brussels. Outside, the autumn leaves blazed in shades of orange and gold, and Europe was still in the throes of post-World War I reconstruction. Inside the lavish meeting halls, some of the greatest names in physics gathered: Einstein, Bohr, Marie Curie, Paul Dirac, Werner Heisenberg, Max Born, Louis de Broglie, and many more. If one were to list the top minds in theoretical physics at the time, nearly all of them were present. Each day's sessions involved formal presentations on the new quantum theory, but the real drama unfolded in the corridors, during breaks, and in the after-dinner discussions. It was during these informal moments that Einstein cornered the younger quantum physicists with incisive thought experiments. He sought to show them that quantum mechanics had internal contradictions, or that it contravened the principle of physical reality. One famous exchange took place after a formal session on wave-particle duality. Einstein approached Bohr, Heisenberg, and Born with a hypothetical. Suppose you have a small hole in a screen, and you allow a single photon to pass through. You place a mirror behind it at a slight angle. By measuring the recoil on the screen, you might determine which path the photon took while still observing an interference pattern. If that were possible, it would break the uncertainty principle. Einstein explained with typical elegance, sketching a diagram on the nearest scrap of paper. He concluded, "Thus, the measurement reveals the path, yet the interference remains. Doesn't that suggest the wave function can't be the full description, or that the principle of complementarity fails?" Bohr furrowed his brow and listened attentively. He was famous for not responding immediately. When he did speak, it was often in a roundabout way, starting with broad statements, then narrowing in on specifics. As the group huddled close, Bohr began explaining how the recoil measurement itself introduced uncertainties in momentum exchange. The result, the path information was never fully ascertainable because the act of measuring recoil disturbed the photon's momentum. Thus, the interference pattern's existence or non-existence would hinge on subtle details that preserved complementarity. Heisenberg piped up, pointing to his uncertainty principle. If you localize the photon to that degree, you lose momentum information. Einstein listened, nodded, and then with a slight grin said, "Perhaps you are correct this time, but I will find a better example." And thus the conference continued. Day after day, Einstein delivered new proposals, sometimes half-formed, sometimes more elaborate. Each time, Bohr retreated to the blackboard or his notes, eventually uncovering an aspect of quantum mechanics or complementarity that resolved the challenge. The other physicists watched in awe, comparing the spectacle to a chess match. Marie Curie observed quietly, never venturing into the quantum controversies herself, but clearly enthralled by the intellectual duel. Paul Dirac, laconic as ever, would simply remark, "We must let the mathematics guide us." Max Born, a close friend of Einstein's, felt torn. He admired Bohr's stance and recognized that Einstein's viewpoint had the weight of an older conceptual tradition behind it. Born later recounted that whenever Einstein seemed close to cornering Bohr, the Danish physicist would come up with a subtle quantum principle that saved the day. In the official sessions, the delegates discussed the new wave mechanics, the Schrödinger equation, and experimental confirmations. Einstein was relatively quiet in these sessions, focusing instead on the deeper conceptual issues. As the conference drew to a close, the general consensus was that the new quantum mechanics had survived Einstein's challenges. Bohr, relieved but also exhilarated, felt more confident in the foundational soundness of his complementarity principle. Einstein, on the other hand, left Brussels with the conviction that the fight was not over. After the conference, Heisenberg wrote to Wolfgang Pauli, "Einstein has shown us that one must be ever vigilant. His challenges sharpen our thinking, but in the end, quantum mechanics stands firm. Perhaps old Einstein is losing some of his cunning." Pauli responded that only a fool would ever discount Einstein's cunning. He might not have prevailed this time, but no one doubted his ability to mount a future challenge. That future challenge arrived in earnest at the Sixth Solvay Conference in 1930. By then, Einstein had refined another thought experiment, the so-called Einstein box. The idea was to measure the energy of a photon precisely by weighing the box before and after emission, thus ostensibly circumventing the time-energy uncertainty relation. If you knew precisely how long the shutter was open and exactly the energy of the photon that left the box, you could measure both energy and time to arbitrary precision, apparently violating Heisenberg's principle. The unveiling of the Einstein box thought experiment at the 1930 Solvay conference is often cited as one of the tensest moments in the Einstein-Bohr debates. Einstein presented the scenario meticulously in front of the assembled luminaries. He explained how the clock inside the box would open the shutter for a predetermined interval, allowing a single photon to escape, and then the difference in mass, via gravitational measurement, would yield the photon's energy. The time of the photon's escape would be known to any desired accuracy, thanks to the carefully calibrated clock. Thus, Einstein concluded, it would seem that the quantum rule about the product of uncertainties, being at least on the order of Planck's constant, is evaded. Bohr appeared visibly distressed. Legend has it that he spent a restless night in the hotel, pacing back and forth, rethinking the scenario. He scribbled arguments on hotel stationery, muttering to himself. By morning, Bohr arrived at the conference prepared. During the next session, Bohr argued that the act of weighing the box in a gravitational field introduced an uncertainty in the time measurement itself. According to general relativity, raising or lowering the box in a gravitational potential well would alter the flow of time measured by the clock. This effect, though tiny, was enough to preserve the time-energy uncertainty relation. The entire scheme, Bohr concluded, was thus consistent with quantum mechanics. Einstein, upon hearing the argument, paused in surprise, smiled, and is said to have remarked, "Well, perhaps I have been wrong," or "Then God does play dice," depending on which historical account one reads. This theatrical parry and riposte sealed the sense among the younger generation that Bohr had emerged victorious again. But to reduce the debates to a point tally would be misleading. Einstein was no sore loser. He believed that if quantum mechanics was truly complete, it would hold up under the most extreme tests. His challenges, though they failed to overthrow quantum theory, served to refine and deepen it, forcing Bohr and others to articulate the conceptual underpinnings more rigorously. The Solvay Confrontations of 1927 and 1930 thus became legendary in physics lore, a clash of titans, Einstein, the restless realist, versus Bohr, the philosophical pioneer of complementarity, yet the debates did not end there. They would evolve into more formal statements, culminating in the famous EPR, Einstein-Podolsky-Rosen paper, and Bohr's subsequent response, a confrontation that many see as the true apex of their dispute. Chapter 4. Thought Experiments and Paradoxes. As the 1930s began, the realm of quantum mechanics was, in many ways, stabilizing. Heisenberg's and Schrödinger's formulations had been shown to be mathematically equivalent. Dirac's transformation theory further unified the field, and quantum mechanics was steadily integrated into the study of atomic, molecular, and even nuclear physics. Yet on the conceptual side, storms still brewed. Einstein felt deeply that, while the theory was extraordinarily successful, it was not complete. Incomplete, in Einstein's mind, meant that quantum mechanics omitted underlying variables or elements of reality that would reintroduce determinism and objective states. He was not alone in his discomfort. Erwin Schrödinger, who had introduced wave mechanics in 1926, shared some of Einstein's concerns. Schrödinger famously illustrated the oddities of quantum mechanics with his cat paradox in 1935, though that scenario was more aimed at the measurement problem and the notion of superposition than at local realism. Still, the Schrödinger cat thought experiment symbolized the uneasy feeling that quantum mechanics, for all its success, painted a bizarre picture of how measurement affects the system under observation. Einstein, for his part, continued to refine conceptual traps, experiments that might reveal an underlying classical reality or highlight an inconsistency in quantum theory. These were typically couched as hypothetical situations. For instance, he imagined an apparatus that split a beam of light into two paths, measuring interference in one path while gleaning which path information from the other path, an idea reminiscent of the 1927 confrontation. Each time, the quantum formalism's defenders pointed to an uncertainty principle or a complementarity argument that closed the apparent loophole. Yet these debates were more than intellectual games. They reached into the heart of what it meant to do physics. Was the purpose of physics purely to correlate measurement outcomes? Or did it aim to describe an external reality, one that persisted independent of observations? Einstein was firmly in the second camp, believing that nature existed in a definite state, no matter how little we knew about it. Bohr, conversely, believed that the concept of a definite state was not well defined without specifying how one observed it. In the quantum realm, the boundary between observer and system was not just a matter of convenience, but essential to the phenomenon itself. A frequently recounted story has Einstein presenting a version of the two-slit experiment to illustrate how one might, in principle, measure the slit the electron goes through while retaining an interference pattern. After a flurry of blackboard derivations, Bohr or Heisenberg would point out that the measuring device's recoil introduced an uncertainty that destroyed the interference. Another anecdote involves Einstein persistently reintroducing the idea of hidden variables, a notion that all quantum probabilities might be the result of some deeper but undiscovered deterministic parameters. These suggestions were largely overshadowed in mainstream physics by the triumphant success of the quantum theory as it was. However, a critical turning point occurred in 1935 when Einstein, together with Boris Podolsky and Nathan Rosen, published the paper known as Can Quantum Mechanical Description of Physical Reality Be Considered Complete? The EPR paper. This was not just another thought experiment. It formalized Einstein's argument for incompleteness. If quantum mechanics was correct, it implied a strange form of action at a distance, or what Einstein scornfully called spooky action at a distance. The EPR scenario involved two particles that interacted and then flew apart. If one measured a property, say position, of one particle, the other particle's corresponding property, momentum for instance, became defined instantly, no matter how far away it was. This seemed to violate locality, a core principle that no influence can propagate faster than the speed of light. For Einstein, the resolution was that quantum mechanics must be incomplete. There had to be some hidden parameters that both particles carried after interaction, ensuring consistent but local behavior. For Bohr, this argument was misguided because it presumed that these properties existed independently of measurement. From Bohr's perspective, the measurement on one particle set the context in which the entire quantum system, the entangled pair, existed, thereby defining the corresponding property of the other particle without requiring any faster-than-light signal. This was not an action on the second particle. It was, rather, the correlated manifestation of a single, holistic quantum state. It was in the EPR debate that the terms entanglement, coined by Schrödinger, and completeness found their rightful place in the physics lexicon. For the younger generation, especially those forging the path of quantum field theory and nuclear physics, the EPR argument seemed either irrelevant or misguided. The operational success of quantum mechanics overshadowed philosophical concerns. But Einstein was unwavering. He would say, The success of a theory does not prove that it is final. Still, the immediate reaction to EPR in the physics community was muted, aside from Bohr's swift rebuttal in the same journal. Bohr's response was technical and dense, but it insisted that no element of reality could be ascribed to a property that was not measured. The upshot was that quantum mechanics, in his view, remained both correct and complete, albeit in a sense that defied classical thinking about locality and reality. Thus, the EPR argument became the new focal point of the Einstein-Bohr debates. It was more subtle than the earlier Solvay thought experiments, more profound and more polarizing. Future generations would pick up the thread, eventually leading to John Bell's theorem in 1964, which tested Einstein's local realism against quantum entanglement experimentally. But in the 1930s, no such test existed, and the world was edging into a global crisis. As the Great Depression spread and the specter of another world war loomed, fundamental physics would soon be overshadowed by political upheaval. Before that overshadowing was complete, Einstein and Bohr exchanged letters about EPR. These letters, brimming with cordial salutations, yet unwavering disagreements, reveal a great deal about their personalities. Einstein, self-assured but never arrogant, laid out his philosophical reasons for rejecting a purely probabilistic reality. Bohr, polite yet firm, reiterated that such classical demands no longer held at the quantum level. The personal tone remained respectful, reflecting the genuine regard they shared. Thus, while the public might have seen them as enemies locked in intellectual combat, those closest to them knew better. In private, Einstein and Bohr could share a laugh, reminisce about their earlier days, or admire each other's insights. Yet on the question of quantum foundations, they remained irreconcilably distant, each holding a position that was well supported by their different conceptual temperaments and guiding philosophies. Chapter 5. The Defense of Reality. Einstein's stance on quantum mechanics, often summarized by his famous line, "God does not play dice," was rooted in a philosophical outlook known as realism. In short, Einstein believed that physical objects possessed definite properties, like position, momentum, spin, etc., independent of observation. This was not a dogmatic stance, but one arising from his deep convictions about the aims and successes of classical physics. Early in Einstein's career, he had used the concept of invariance in relativity to demonstrate how certain aspects of reality remained consistent across reference frames. His entire worldview was built on the notion that there exists a robust external reality that does not vanish or morph arbitrarily, depending on whether or how someone chooses to observe it. In classical physics, one can measure position and momentum to arbitrary precision, limited only by experimental skill, not by an intrinsic barrier. Einstein never lost faith that such determinism existed at a deeper level, even if quantum theory prevented direct measurement. To Einstein, quantum mechanics was a profoundly successful algorithm, capable of predicting outcomes to exquisite accuracy. But as a final description of nature, he saw it as incomplete. He reasoned that if the wave function was truly the complete description of reality, then we faced paradoxes like entanglement, where measurement at one location instantly influenced the state of a distant partner. That made no sense in light of special relativity, which held that no influence could travel faster than light. Hence, his call for hidden variables, unobservable parameters that would restore a kind of local realism. While Einstein himself never fully formulated a hidden variable theory, he believed strongly that the ultimate job of physics was to discover one. In private conversations, he suggested that perhaps a deeper field theory might unify quantum phenomena with a deterministic structure, echoing how Maxwell's field equations had once replaced the older action-at-a-distance laws of electromagnetism. One of Einstein's often overlooked arguments hinged on causality. He would say that nature must have consistent causal chains. If quantum mechanics was truly fundamental, causality seemed to break down into pure probabilities. While probabilities were not foreign to physics, statistical mechanics had used them for decades. They always arose from incomplete knowledge, not a fundamental indeterminism. For Einstein, the idea that nature itself was fundamentally random in the sense that outcomes had no deeper cause was deeply unsatisfying. Even in the face of Bohr's repeated demonstrations that quantum mechanics consistently evaded contradiction, Einstein held firm. He once wrote to Max Born, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory yields much, but it hardly brings us closer to the secret of the old one." That old one, a term Einstein liked to use for God or nature, was for him an emblem of a coherent cosmic order. Historically speaking, Einstein's realism had deep roots going back to pre-Socratic Greek philosophy, which posited that nature had an objective existence governed by laws. Bohr's viewpoint, or the so-called Copenhagen approach, many found reminiscent of Kantian ideas, where the structure of our knowledge was shaped by the categories of our understanding, in quantum theory, the measurement choices. Einstein, however, was more in line with the Enlightenment ideals of rational realism, championed by Newtonian mechanics for centuries. By the mid-1930s, Einstein's frustration with the quantum orthodoxy had grown. He could not fault its predictive power. He recognized it as one of the greatest triumphs of physics. But for him, it was not a permanent settlement. "One day," he mused to a colleague, "we shall see the next revolution in physics, which will place quantum theory upon a deterministic bedrock." That revolution, however, never came in Einstein's lifetime. The EPR paradox, instead of dethroning quantum mechanics, would later become a gateway to even more astonishing findings, like Bell's theorem and the experimental confirmation of quantum entanglement. Though Einstein did not live to see those developments, his unwavering defense of reality left a permanent mark on the philosophical discourse surrounding quantum mechanics. Whenever modern physics touches upon interpretations, be it many worlds, de Broglie-Bohm pilot waves, or objective collapse theories, the spirit of Einstein's questions resonates. Was he right that quantum mechanics was incomplete? Or was Bohr correct that the question itself was misguided? At the time, Einstein believed he was standing up for the deeper ideals of physics, that we must not rest until we have a coherent picture of the world, free of logical paradoxes or reliance on the magic wand of measurement. In that sense, he saw Bohr as too willing to discard classical logic, too eager to enshrine observer-dependent realities as fundamental. He did not demean Bohr's intelligence. In fact, he deeply respected it. But he felt Bohr and his followers had capitulated too soon to the notion that nature was fundamentally opaque to rational analysis beyond probabilities. The rest of the world, especially as the 1930s turned into the 1940s, increasingly turned its attention to larger geopolitical events. Nazi Germany's rise to power forced Einstein, who was Jewish, to leave Europe for Princeton in 1933. Bohr, also threatened by the Nazi regime, though for partly different reasons, would eventually flee to Sweden and then to the United States, contributing to the Allied war effort. The debates about quantum mechanics receded into the background, overshadowed by the urgency of global conflict and the dawn of the nuclear age. Yet, Einstein, safe in Princeton's Institute for Advanced Study, never stopped thinking about the problem of quantum completeness, even as he worked on unified field theories that gained little traction among mainstream physicists. Chapter 6. The Language of Nature. For Niels Bohr, the question was not whether quantum mechanics was incomplete, but how best to describe its irreducible features. He believed that the challenge lay in the fact that human language and concepts evolved to deal with a classical world of tangible objects and well-defined properties. Quantum phenomena, by contrast, operate in a regime where the classical categories of position, momentum, wave, or particle lose absolute meaning. Bohr often employed the notion of phenomena to highlight that quantum mechanics deals strictly with observable outcomes of experiments, each outcome requiring a particular experimental setup. If you design an apparatus to measure wave-like interference, you lose all information about particle paths. If you design an apparatus to measure which path information, you lose the interference pattern. This complementary relationship was, for Bohr, not a minor technical detail, but the essence of the new physics. He spent considerable time trying to articulate his philosophy, culminating in the principle of complementarity. Bohr posited that wave and particle properties were complementary aspects of the same underlying reality, aspects that could never be simultaneously observed. Like the two sides of a coin, you could see heads or tails, but not both at once in a single view. For Bohr, this was not just a matter of practical limitation, but a fundamental statement about nature. When Einstein confronted him with the EPR paradox in 1935, Bohr's reply hinged on the idea that the elements of reality that Einstein, Podolsky, and Rosen ascribed to the unmeasured subsystem did not have the definitional basis Einstein presumed. Bohr wrote that the entire argument rests upon an ambiguity in the interpretation of the measurements. He pointed out that quantum mechanics does not speak about what is the case prior to measurement, but only about what can be said regarding the outcomes of measurements once they are performed. In that sense, the EPR criterion for reality, that if one can predict a property with certainty without disturbing the system, that property must be real, was from Bohr's vantage too classically rooted. Unlike Einstein, Bohr was comfortable with the idea that quantum mechanics might defy classical logic because classical logic was gleaned from everyday macroscopic experience. Perhaps the logic of microphysics was inherently different. There is no quantum world, Bohr once reportedly said to a colleague. There is only an abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. Though the authenticity of that quotation remains debated, it certainly captures Bohr's perspective as recounted by many who studied under him. This emphasis on the what we can say aspect made Bohr, in Einstein's eyes, dangerously close to embracing subjectivism. But Bohr denied that. He insisted that objective reality still existed, but only in the sense that measurement outcomes were objective once they occurred. The wave function, in his eyes, was not an objective representation of reality, but rather a symbolic tool for predicting measurement outcomes in certain experimental conditions. These arguments about the meaning of the wave function, the measurement problem, and the role of the observer sowed seeds that would later blossom into interpretive battles among future physicists and philosophers. Yet in the 1930s, Bohr's interpretation held sway, partly because it was championed by other influential figures, Heisenberg, Pauli, and Born among them, and partly because no competitor interpretation offered better predictive or explanatory power. Bohr's nearly obsessive attention to the philosophical nuances sometimes exasperated even his closest colleagues. Wolfgang Pauli, known for his quick wit, once quipped in exasperation, "If I understand what Bohr says in the morning, I can't understand what he says in the afternoon." Despite the confusion, Bohr's conviction that quantum mechanics demanded new categories of thought gained widespread acceptance in the face of the theory's stunning empirical success. By the time World War II approached, Bohr had become not just a leading physicist, but a statesman of science. His institute in Copenhagen was internationally recognized as a hub of quantum research. Younger physicists, especially those bridging nuclear physics and quantum theory, found in Bohr an intellectual and moral leader. Indeed, Bohr's own work on nuclear fission, with John Wheeler in the United States, helped clarify how atomic nuclei could become unstable and split, releasing tremendous energy. This research was a stepping stone to the Manhattan Project, albeit one Bohr approached with moral ambivalence. All the while, the tension between Bohr's perspective and Einstein's realism simmered in the background. Letters flew across the Atlantic, with Einstein in Princeton and Bohr in Copenhagen. Although the war made communication sporadic, they still managed to share cordial notes or short treatises on quantum mechanics. Neither man budged from his fundamental stance. Bohr continued to emphasize that any property of a quantum system emerges only through the interaction with a measuring apparatus. Einstein refused to concede that no deeper reality underlay these phenomena, telling Bohr in one letter that the geometry of space should not depend on the instruments we use, any more than the basic structure of matter should vanish when we decide not to look. And yet, there was no rancor. Both revered the other's contributions to physics. Both recognized the deep sincerity in the other's position. Their debates, though pointed and unyielding, retained a spirit of mutual respect that is often missing in lesser scientific quarrels. It was, in many ways, an ideal form of disagreement, one that advanced scientific thought, sharpened philosophical inquiry, and left an enduring legacy for future generations to explore. Chapter 7. Friends in Opposition. Albert Einstein and Niels Bohr did not see each other as enemies. Rather, they occupied two poles of a fundamental conversation about the nature of reality, forging a bond that was paradoxically strengthened by their disagreements. They were akin to explorers climbing different faces of the same mountain, each convinced of their vantage point, but also deeply appreciative of the other's brilliance. On a personal level, Bohr admired Einstein's individualism and imaginative leaps, recalling how it was Einstein's 1905 paper on the photoelectric effect that had effectively launched quantum theory into the limelight. Indeed, Bohr would tell younger colleagues, "We are all indebted to Einstein for teaching us how to think about quanta." Einstein, for his part, lauded Bohr's insight into atomic structure and recognized that the Bohr atom was an essential stepping stone to the new quantum mechanics. He once wrote, "Bohr is a man of unquestionable perspicacity." Their personal interactions were often warm and sprinkled with humor. At conferences, if a discussion became too intense, they might slip away to dine together or stroll in a nearby garden, carrying on their conversation in a more relaxed setting. One anecdote from the 1930 Solvay conference has them sitting in a quiet corner after dinner, each sipping a small glass of spirits, reflecting on the philosophical implications of the day's debate. Bohr, as usual, turned the conversation into a deeper reflection on knowledge and language. Einstein listened patiently, occasionally interjecting with remarks about the necessity for a physical model. They parted that night with a friendly handshake, both aware that they remained miles apart in their conclusions. This mutual respect also surfaced in their letters. Einstein's letters to Bohr often began with, "My dear Bohr," and ended with cordial regards. He would outline his newest ideas or concerns about quantum theory in meticulous prose, sometimes accompanied by small diagrams. Bohr's replies, typically lengthier and more circuitous, were equally friendly, though Einstein was known to joke that after reading Bohr's letters, he sometimes needed a nap to process them. Colleagues who witnessed these interactions reported a curious dynamic. Bohr sometimes seemed almost deferential to Einstein, given Einstein's earlier, epical contributions, while Einstein displayed a fatherly affection for Bohr, the younger man, even though Bohr was only 8 years his junior. They had a rapport that allowed them to critique each other's work without fear of personal offense. During the 1930s, with Europe slipping into political turmoil, their shared concerns about the rise of fascism overshadowed purely scientific debates. Einstein, horrified by the situation in Germany, emigrated to the United States in 1933. Bohr tried to maintain an environment of scientific openness in Copenhagen, but eventually fled in 1943, fearing arrest by the Nazi occupiers. They both ended up contributing, directly or indirectly, to the Allied war effort. Einstein by signing the famous letter to President Roosevelt that led to the Manhattan Project, Bohr by offering insights into nuclear fission. Despite the weighty moral dilemmas each faced, their discourse on quantum theory continued, albeit in more sporadic fashion. In 1939, Bohr visited Princeton briefly. While there, he and Einstein spent time discussing the new developments in nuclear physics. Observers recall a moment when they were both in front of a blackboard in Einstein's office. Einstein was describing a possible unified field approach, while Bohr countered with comments about how quantum phenomena were essential even in nuclear processes. The chalk dust on their sleeves, the glow of the overhead lamp, and the thick accent of Bohr blending with Einstein's as they volleyed ideas back and forth formed a tableau of scientific camaraderie. "If only we had recorded it," lamented one of the young onlookers. One must note that while the two men were often at odds intellectually, their shared plight as exiled intellectuals, forced to watch Europe burn, forged a certain solidarity. They both had Jewish ancestry, though Bohr's mother was Jewish and Einstein was wholly Jewish. They both grieved the disintegration of European centers of learning that had nurtured them. They each used their influence, as far as they could, to assist displaced scientists seeking refuge. In the final analysis, friends in opposition is an apt description. Their debates were never petty, never personal. They were each driven by a passion for truth, albeit perceived from different vantage points. Long after the war, after Bohr had returned to Copenhagen and Einstein had settled in Princeton, they continued to correspond occasionally. Even in Einstein's final years, he died in 1955, one sees letters to Bohr rehashing quantum conundrums, sometimes referencing new developments. Each letter ends with sentiments that reveal a deep bond. If there was any sadness in their relationship, it was perhaps that they could never fully convince each other. That unresolved tension, however, became a fertile ground for subsequent generations who would wrestle anew with the philosophical dimensions of quantum theory. In the end, Einstein and Bohr showed the world that great minds can clash with genuine civility and mutual admiration, a legacy that stands as tall as their scientific contributions. Chapter 8. The Legacy of Entanglement. Einstein, Podolsky, and Rosen's 1935 paper had introduced a new dimension to the debates: entanglement. Schrödinger coined that term to describe the peculiar linkage of quantum states. The EPR argument took center stage, overshadowing earlier thought experiments. Physicists in the immediate aftermath recognized that EPR raised the puzzle of non-local correlations, but few recognized how significant it would be for the future of physics. Bohr's response to EPR was immediate and forceful, asserting that Einstein's premises were flawed. However, Bohr's explanation did not fully eliminate the conceptual cloud. Many simply accepted Bohr's argument that quantum mechanics was consistent and that the notion of incomplete reality was misguided. For practical physics, calculating spectra, cross-sections, nuclear reactions, that was enough. The theoretical machinery worked. Yet the question lingered: could quantum entanglement produce real physical effects that defy classical locality? Were these correlations simply a matter of incomplete knowledge, or did they reflect a fundamental aspect of reality? At the time, the technology did not exist to test entanglement on a large scale. Single photon or single atomic measurements were in their infancy. The debate thus remained mostly philosophical, overshadowed by the urgencies of World War II and the subsequent Cold War. Einstein's latter years saw him trying unsuccessfully to formulate a unified field theory that would integrate gravitation and electromagnetism, hoping perhaps that it might also provide an underpinning for quantum phenomena. He never succeeded. The mainstream of physics moved toward quantum electrodynamics and then quantum field theory, culminating in the Standard Model of particle physics decades later. Einstein remained an outsider to that mainstream. He was revered, but many younger physicists felt he was out of touch with modern methods. Einstein was not bitter. He simply believed that the future would vindicate his quest for a deeper theory. Niels Bohr, after the war, returned to Denmark and presided over the continuing development of quantum theory, albeit with a focus on nuclear physics and the emerging puzzle of elementary particles. He recognized that Einstein's criticisms had been instrumental in shaping a clearer formulation of quantum mechanics. But by the 1950s and 1960s, most physicists took the success of quantum theory as evidence that Bohr's complementarity viewpoint was essentially correct. Einstein's reservations were acknowledged, but commonly treated as philosophical niceties that had little bearing on practical research. The next major shift came with John Stuart Bell. In 1964, Bell published a theorem showing that no local hidden variable theory could reproduce all the predictions of quantum mechanics. If the quantum mechanical predictions of certain correlation measurements, like those in spin or polarization entanglement, were correct, then local realism could not hold. This was a direct response to EPR and to Einstein's dream of a local hidden variable theory. Bell's theorem was couched in precise mathematical inequalities, Bell inequalities, that experiments could test. When Bell's theorem was first published, it did not immediately set the world on fire. But over the following decades, experimentalists, starting with John Clauser and Stuart Friedman in the early 1970s and continuing with Alain Aspect in the early 1980s, performed tests with entangled photons. Their results violated the Bell inequalities in ways consistent with quantum mechanics, thus ruling out local hidden variable theories. Over the next decades, more refined and loophole-free experiments further confirmed these violations, culminating in the 21st century's advanced experiments with entangled photons spanning hundreds of kilometers. What did this mean for Einstein's viewpoint? Strictly speaking, these experiments proved that if one assumes realism and locality, you cannot recover all the predictions of quantum mechanics. One must abandon at least one, either accept non-locality or abandon the notion of realism, or adopt a very unconventional interpretation. Many found themselves either leaning toward a non-local interpretation, such as the Bohmian pilot wave approach, or adopting an instrumentalist stance, reminiscent of Bohr, that the question of underlying realism is moot. Some have even explored many worlds, or relational interpretations that circumvent classical realism in different ways. Thus, the EPR debate, far from being a historical footnote, ignited an entire subfield of foundational research that blossomed into quantum information theory and quantum computing. In a sense, Einstein's challenge propelled the exploration of entanglement, which today is recognized as a resource for quantum cryptography, quantum teleportation, and quantum computers. The irony is that Einstein's attempt to show the incompleteness of quantum mechanics ended up unveiling its most profound and fascinating aspect: entanglement. Bohr did not live to see the Bell tests. He died in 1962. Einstein, who died in 1955, never saw them either. Had they witnessed these experiments, one can only imagine their reactions. Einstein might have lamented that nature truly appeared to play dice at a non-local level. Bohr might have nodded and said it confirmed that the classical notion of locality was not absolute, but we can be certain that, had they been alive, the conversation would have continued, generating new thought experiments and analyses. In the grand tapestry of physics history, the Einstein-Bohr debates stand out as a defining moment when science encountered the limits of classical thinking. The two protagonists represented not just differing scientific hypotheses, but contrasting philosophical commitments about the nature of reality and the role of measurement. Entanglement was the legacy of that debate, a phenomenon that continues to challenge our intuitions and fuel new discoveries. Chapter 9. Quantum Shadows in the Cold War. While the seeds of quantum entanglement research were germinating in post-war laboratories, the broader context of physics during the Cold War focused on nuclear weapons, radar, solid-state electronics, and eventually space travel. The quantum mechanical tools developed by the Bohr-Heisenberg-Schrödinger generation were harnessed for practical engineering feats: transistors, lasers, nuclear reactors, and more. In that period, Einstein's iconic status grew further, especially after the atomic bomb made real the destructive potential of modern physics. His face, with its trademark unruly hair, became the emblem of genius, while Bohr's image remained more confined to academic circles. Yet within the scientific community, Bohr's institute in Copenhagen remained a pilgrimage site for theorists. Some moral tensions emerged. Bohr had contributed to nuclear research and later advocated international collaboration and open exchange of scientific knowledge, hoping to prevent the misuse of atomic energy. Einstein, for his part, regretted signing the letter to Roosevelt that led to the Manhattan Project, famously stating that if he had known the Germans would fail to develop an atomic bomb, he would never have recommended the US pursue it. Neither man was directly involved in the actual building of the bomb, but their intellectual legacies had paved the way for an era of nuclear standoff. The Einstein-Bohr debates themselves, however, were overshadowed by the arms race, the race to space, and the swirling politics of East versus West. Within academic circles, the question of quantum foundations never fully died. In Soviet Russia, certain interpretations of quantum mechanics were favored as they were seen to align, or not, with Marxist-Leninist philosophy. In the West, the dominant stance was more pragmatic. "Shut up and calculate," as the phrase, often attributed to David Mermin, though apocryphally, succinctly put it. Quantum mechanics worked, so why fret about interpretational niceties? Yet pockets of foundational research persisted. John Bell, working at CERN, was a notable figure. While his day job involved accelerator physics, his mind was always on the deeper issues of quantum theory. In the US, philosophers of science and a handful of physicists quietly kept the Einstein-Bohr debates alive in seminars and academic papers. By the 1960s, Eugene Wigner, Henry Stapp, and others started exploring the measurement problem again, questioning consciousness's role in wave function collapse, a line of inquiry reminiscent of Bohr's emphasis on the observer. Curiously, in the Soviet Union, physicists like Lev Landau and Yakov Frenkel took a more mathematical approach, focusing on formal aspects of quantum field theory, while the philosophical realm was often mired in ideological constraints. Still, the echoes of Einstein and Bohr resonated. The very fact that quantum mechanics was never replaced by a more deterministic theory during the mid-20th century underscores how robust it was. Even attempts like David Bohm's pilot wave theory, a hidden variable approach that introduced non-locality, never gained broad acceptance, partly due to the complicated nature of the formalism and partly due to ideological biases within mainstream physics. In this environment, Einstein's quest for completeness and Bohr's principle of complementarity took on almost mythic status. Graduate students would hear the stories of the Solvay conferences, perhaps dramatized by their professors, and come away with the sense that quantum mechanics was underpinned by an unresolved philosophical puzzle. Some embraced that puzzle, others found it irrelevant to practical laboratory work. By the late 1970s, when the Friedmann-Kleuser experiment confirmed the quantum violation of a Bell inequality using entangled photons, the results signaled that if Einstein's local realism were to hold, the predictions of quantum mechanics would be incorrect. Instead, the data matched quantum mechanics. Slowly, this trickle of experimental results grew more refined. In 1982, Alain Aspect's experiments in Orsay, France, removed certain loopholes, making it increasingly difficult for local hidden variable models to survive. The news spread, the quantum predictions, and thus Bohr's perspective on the non-local correlations were empirically upheld. Yet, ironically, Bohr's own philosophical interpretation was not simply validated by these experiments either, because Bohr never exactly claimed that quantum mechanics was non-local in the sense of signals traveling faster than light. Instead, Bohr had argued that the very concept of separable subsystems breaks down for entangled states. The experiments simply showed that if one tries to maintain local realism, the quantum predictions are violated. This was consistent with Bohr's complementarity but did not precisely confirm Copenhagen over other non-local interpretations. Ultimately, the Cold War era ended with quantum mechanics triumphant, powering the emerging technologies of integrated circuits, atomic clocks, and lasers. The Einstein-Bohr debates, overshadowed in the public eye by the bomb and space race, endured among those who dared to question the deeper philosophical meaning of the theory. By the time the Iron Curtain fell in 1989, a new generation of physicists was poised to transform quantum weirdness into technology, quantum cryptography, quantum computing, and quantum teleportation. All these developments hinged on entanglement, the phenomenon that Einstein had highlighted as problematic. History can be ironic. Chapter 10. The Verdict of Time. Today, as the 21st century moves forward, the Einstein-Bohr debates are far from a dusty historical curiosity. They continue to inform ongoing research into the nature of reality, quantum information science, and even emergent technologies. Modern experiments with entangled photons, atoms, and superconducting qubits have become increasingly sophisticated, confirming quantum predictions in scenarios Einstein might never have imagined. Quantum entanglement, once a theoretical oddity, is now recognized as a resource for quantum computing, providing the basis for qubits to exhibit massive parallelism in certain tasks. Quantum cryptography leverages entanglement to detect eavesdroppers. Quantum teleportation, a demonstration of transferring quantum states across space using classical communication plus entanglement, has traveled from being a whimsical notion to an established experimental protocol. In each of these advances, one sees the ghost of Einstein's original critique. Could nature really be so bizarre that instantaneous correlations exist without a classical mechanism? The empirical answer is yes, with the caveat that these correlations cannot be used to send faster-than-light signals or violate causality. Nonetheless, the brand of locality that Einstein defended is at odds with the proven quantum correlations. The verdict of experiments, from Clauser-Friedman to Aspect to the latest loophole-free tests, consistently upholds quantum mechanics over local realism. But does that mean Bohr was entirely correct? Some argue that Bohr's language-centered, observer-centric approach is not fully fleshed out as a rigorous interpretation. Others find solace in alternative frameworks such as many worlds, relational quantum mechanics, or Bohmian mechanics, which either accept non-local hidden variables or interpret wave function collapse as an illusion. Yet, in all these interpretations, the main point stands: quantum phenomena do not conform to a classical worldview. That was Bohr's fundamental stance, and in that sense, the debates ended up leaning in Bohr's favor, at least in terms of what predictions nature abides by. Philosophically, however, Einstein's quest remains alive. The question of whether quantum mechanics is truly a final theory or might be subsumed by a deeper theory, such as a theory of quantum gravity that might unify general relativity and quantum field theory, lingers. There are hints in string theory, or loop quantum gravity, that space-time itself could be emergent from quantum information. If a future radical theory emerges, it might incorporate quantum mechanics as an approximation, just as quantum mechanics once incorporated classical mechanics. Would that new theory restore some notion of realism? Or would it push even further into non-intuitive domains? We do not yet know. What is certain is that the Einstein-Bohr debates set a standard for intellectual rigor and respectful disagreement. They forced physicists to acknowledge that scientific theories have philosophical implications that cannot be brushed aside. The dialogues, from the Solvay conferences to the EPR paper, remain a masterclass in how to handle fundamental disagreements. Neither Einstein nor Bohr stooped to ad hominem attacks or polemics. They stuck to logical arguments, thought experiments, and open discourse, forging a template for scientific inquiry at its highest level. If we look to the personal dimension, we see that both men died respected, beloved, and somewhat misunderstood. Einstein's final days in Princeton were spent quietly working on a unified field theory that never quite materialized. He remained convinced that quantum mechanics, while correct in the phenomenological sense, would eventually be superseded. Bohr, returning to Copenhagen, maintained that the lessons of quantum mechanics about complementarity and measurement were among the greatest intellectual achievements of the 20th century. If the two men were still around to witness the continuing developments in quantum information, one can imagine them locked in yet another cordial but pointed conversation. In retrospective summation, the debates can be viewed as a clash of conceptual paradigms. Einstein's paradigm was that of an external reality with well-defined properties and local interactions, an extension of classical realism into the relativistic domain. Bohr's paradigm was that of an interactive reality, in which experimental setups and measurement contexts define what can be said about the system. Quantum mechanics, as discovered, seemed to vindicate Bohr operationally, Yet it also raised deep questions that remain partially unanswered. A final reflection might be borrowed from John Wheeler, a later giant of theoretical physics, who once said, "Useful as it is under everyday circumstances to say that the world exists out there, independent of us, that view can no longer be upheld." There is a strange sense in which this is a participatory universe. Bohr might have smiled upon hearing that. Einstein, likely, would have raised a skeptical eyebrow. And so the story continues. The verdict of time is that quantum mechanics stands triumphant in every experimental test. Local realism, as Einstein championed it, has been refuted as a fundamental principle. Yet the deeper truth behind quantum phenomena remains elusive. In that sense, Einstein's dissatisfaction continues to haunt the field, ensuring that no physicist can wholly ignore the conceptual underpinnings of quantum theory. Meanwhile, Bohr's emphasis on the interplay between experiment and theory set the tone for how modern science regards the boundary between observer and observed. The Einstein-Bohr debates, therefore, have no simple resolution. They form an eternal dialogue that sits at the heart of physics' most perplexing questions. Whether in the hush of a lab late at night or in the hustle of a theoretical colloquium, the spirit of that dialogue endures. The men themselves are gone, but their intellectual footprints remain deeply etched into the foundation of modern science, reminding us of the power of respectful, passionate argument in the pursuit of truth, and the humbling realization that nature may be stranger than any of us, even Einstein, ever imagined. Epilogue. The ever-receding horizon. In the end, the story of Albert Einstein and Niels Bohr is not merely the tale of two great scientists locked in disagreement. It is the story of physics confronting its own conceptual limits and expanding its language to accommodate a new kind of reality, one in which probability, measurement, and entanglement upend centuries of classical assumptions. As we look back on the Solvay conferences, the EPR paradox, and the exchange of letters, we see a saga that blends personal friendship, philosophical profundity, and scientific revolution. Einstein offered the vantage point of a deep realist tradition, shaped by the success of classical and relativistic physics. Bohr introduced a radical reinterpretation that accepted quantum phenomena on their own terms, challenging conventional ideas of objectivity and determinism. Their debates were not settled by rhetorical flourish, but by the patient, cumulative weight of experimental results and theoretical elaboration in the decades that followed. Yet the horizon keeps moving. Each new insight in quantum foundations or quantum gravity shifts our understanding, introducing new layers of complexity. If Einstein or Bohr were alive today, they might well debate whether quantum computing truly leverages superpositions in ways that confirm Bohr's complementarity, or whether some deeper hidden structure might yet surface. Thus, the Einstein-Bohr debates remind us that science is a human endeavor, driven by the interplay of ideas, personalities, and the irrepressible desire to understand the cosmos. Their legacy stands as a beacon that lights the path of inquiry, showing how conceptual revolution often arises from the tension between established norms and iconoclastic questioning. And so, we continue forward, guided both by Einstein's restless quest for a deeper reality and by Bohr's patient insistence that we must learn to speak the language that nature itself reveals, no matter how foreign it may seem to classical ears.